Hello. In today's video, we will go over the basics of how to graph two very special types of inverse functions, the exponential and the logarithmic graph. Let's get started. So we begin by recalling that if you have two functions which are inverses of each other, the idea is that when you operate one of them on the other, they should undo the operation, leaving you just with x. So what that would look like graphically, if you recall from previous classes perhaps, would be that your domain and your range are switched for inverse functions. So two special types of inverse functions are exponential and logarithmic functions. So our first bullet point in our notes says the domain of an exponential function is the range of its inverse logarithmic function. So that makes sense to us. We're going to apply that as we start to build these graphs on this slide. So if we look at our graph that represents f of x equals, let's see, b to the x, so our exponential graph here in blue. Looking at this graph here, we see that we have exponential growth whenever our values for b, for our base, are greater than 1. Exponential in the sense that the variable is living in the exponent, so that's one clue that this is exponential growth. But practically speaking, when you multiply a number, a base, times itself repeatedly, you're growing very rapidly, right? For example, if you woke up one day and noticed that you had 5 cockroaches in your home, and the next day you woke up and you checked and now you had 25 cockroaches in your home, and the next day 125 cockroaches. That's terrifying, but that's an example of exponential growth, okay? Where we're multiplying by the base repeatedly. Okay? So if that base, like 5, is greater than 1, we are growing, and we're seeing our graph grow from left to right in the blue graph here on the left side of your screen. Now, 3 easy points that you should remember from your previous classes are when x equals -1, 0, and 1 for your inputs. If you input, for example, -1, and you insert that for your exponent, your input x, we would have our base to the -1 power, which is really just the reciprocal, right? 1 over the base. So for example, in our cockroach example that I made up a moment ago, -1 would have been 5 to the -1, or 1/5. So we would have started off somewhere over here. At an input of -1, I would be at 1/5. On the other hand, what about 0? Well, if 0 is your input and it's in the exponent, any base to the 0 power, as long as that base is not 0 itself, should be 1, right? It's saying I have no multiplication repeating, so I just have a placeholder for multiplication known as 1. So at 0, we're going to be at our base in that graph, in that exponential growth model. And in that case, for the cockroach example, on day 0, I started off with 5 cockroaches, so that would be where I'd begin. Or sorry, well, I should say 1, and then multiply by 5, so I misspoke there. But the idea here is the initial amount will end up being that output. So assuming that there was only 1 cockroach in this graph, that would be at 0, 1. Okay? Now for putting in 1 for our actual exponent here, we would have our base to the first power. The first power is always just the base itself, isn't it? It's really just one copy of that number. So at 1, I'm up here at my base, which could have been 5 if it was the cockroach problem. That's where the 5 was supposed to be. I misspoke earlier. Okay. So with that in mind, I can see that anytime I have a base bigger than 1 and its exponential growth, this blue graph on the left is what is going on in my head. I'm noticing that it's growing exponentially, and many things are modeled this way. Populations of bacteria in a petri dish, a lot of different types of populations do grow exponentially. If you're wondering about the human population, it's not quite exponential because we have a lot of limiting factors. We actually have a certain carrying capacity that we cannot exceed as a planet, so our graph isn't quite exponential. It ends up starting to approach a certain number, and then it has a cutoff. Okay, we haven't quite reached that number yet, so we're okay. All right, so exponential growth means we are growing without any inhibitions, and we are shooting up because we're multiplying repeatedly by our base. On the other hand, we could have exponential decay, which is the blue graph on the right. Now that's going to happen when our base is between 0 and 1. So for example, instead of 5 to the x, maybe 1/5 to the x, or 1/2 to the x. Each time when you multiply by that base repeatedly, you're getting smaller and smaller and smaller. In other words, as your x values get bigger, your y values get closer and closer to, that's right, 0. We'll talk more about that. It turns out that's a horizontal asymptote. We'll talk more about those in the future. And it would be at y equals 0, okay? We mentioned them before in our discussion of rational functions, but that's popping up again. This idea of as x gets really big or really small, is there a certain y value we're approaching? And in this case, it is y equals 0. So we can fill that in as well. And let's go over here, y equals 0. That would be our horizontal asymptote for the exponential growth or decay model. Now, we're finally going to get to talk about its inverse, okay? So the inverse of an exponential model is called logarithmic. And so by logarithmic, what we're really saying is I've switched my x and my y, my domain and my range. So instead of -1, 0, and 1 for inputs, I would use them as my outputs. And you can see that here. I'll switch colors maybe to red to be consistent. So now notice what's happened. If I switched my x and my y, now I get 1 over my base for my input when I have the output of -1. So for example, if I had a logarithm whose base was, let's say, 5, this would mean when I have the output of -1, my input must have been 1/5. So at 1/5, maybe around here, I would be down here at, let's say, -1. 1, 0, because 0, 1 has been switched, so that would be this point on the x-axis, 1 to the right. And then b1, my base 1, instead of 1 in my base. So if my base was 2, I think that's what maybe I said 5, I can't remember now. I think it was 5. If my base was 5, let's say, I would go 5 units to the right. So 5 units to the right, and then I would go up here at 1, okay? So we can see something very interesting if we're paying attention. One thing that we should be noticing is that there is nice symmetry along the line y equals x. Along the line y equals x. There's some nice symmetry going on there. And I think that's one of our blanks here. Let's fill it in here above. We have nice symmetry along the line y equals x. And that's because when the domain and the range have switched, my x's are now y's, my y's are now x's. So the line where x is equal to y would be the line about which we are symmetric. We're folding over that line. So that's very helpful for our graph. We should always be able to graph a logarithm from its exponential inverse and vice versa. So what about the other asymptote? Well, instead of a horizontal asymptote, for a logarithmic graph, I will have a vertical asymptote at x equals 0. And that's because we've switched our domain and range, haven't we? So my vertical asymptote is at x equals 0. So what does that mean? Well, that affects some things. Notice that my logarithmic graph here, which is growing whenever my base is bigger than 1, and here my logarithmic graph on the right is falling or decreasing from left to right whenever my base is between 0 and 1, like a fraction 1/2. So notice what happens, though, for your available inputs. It's no longer the case that you could put any x value into a logarithmic function. In fact, if you look at that red graph, whether it's falling or growing from left to right, you should notice something. That's right. All of your x values are to the right of the vertical asymptote. In other words, they're always bigger than 0. Your inputs must be greater than 0. So from this, I want to make a note here. The argument of a logarithm, which is right here, it's like x in this case, but sometimes it'll be x plus 5 or something different, must always be greater than 0. So we're going to make a note of that, and we'll talk more about that when we discuss domain in more detail later. For these graphs, we should be able to look at the domain and the range and see the nice relationship that inverse functions have. The first thing I notice is for my exponential, the blue curves, the growth and decay, my domain is any input. There are no restrictions. So -infinity to infinity would be my domain. But notice, if it's truly the case that the exponential and the logarithmic graph are inverses of each other, then their domain and their range, their x's and their y's, better swap. So my domain for my exponential graph, the blue ones, should be my range for my logarithmic graph, the red ones. Let's see if that is holding water as we look at the graphs themselves. Well, yeah, take a look at the red graphs, whether it's the increasing or the decreasing logarithm. Notice that you can go down forever or up forever, slowly, but you can still go up to every output possible. So that is making sense that they are in fact inverses of each other. The domain and range are switching for the inverse functions. Similarly, if I were finding the range of my, of my exponential model, notice there are some y values, some outputs that we don't reach. Namely, we never actually get to 0 for y, do we? We're always right above 0. So parentheses, meaning you're not including it, 0 toward infinity. You're allowed to go up forever in this way, and in this, to the left forever, you're going up forever as well on the right. Now, what about the relationship then with the domain of the logarithmic function? Let's take a look. We're expecting the same thing to hold, right? If they're truly inverses, this should be 0 to infinity. Let's see if that makes sense. If I look at the red logarithmic graphs on the left and the right, we notice the vertical asymptote made it be the case that every input had to be to the right of 0. So that is, in fact, 0 to infinity, isn't it? All right. So one of the other things we want to point out, besides the graphs, which we're going to be playing with a lot today, we want to also notice that sometimes we won't write the name of the base for our logarithm. Sometimes instead of base 2 or base 5 or base 1/2, we'll actually leave it blank. And if I leave it blank and it was log, you are knowing that that is implied, you should know that that is implied to be base 10, base 10. It's called a common log. On the other hand, if you see ln, we read that as natural log, which is implied to have base e, Euler's number, where e is kind of like pi. It's an irrational constant that exists in nature. It was discovered, and it goes on forever with no repetition or pattern. So 2.71, something like that, okay? You don't have to memorize it. There's an E button. You don't have to memorize the part of it anyway. There's an E button on most of your scientific and graphing calculators, so you can have that to help you. Okay, so finally, let's get started graphing transformations of these functions, keeping in mind that you must have 3 points in mind before you can move them around. Okay. All right, so let's get started with our graphs. We're going to be graphing exponential functions and then some logarithmic functions. Here we go. So to begin, we're going to be sketching the graph of f of x equals 3 to the x minus 1, being careful to show 3 points, the asymptote, and then discuss its domain and range. So the first thing that I like to do when I start these problems is to figure out what kind of model I have. So is it linear? Is it quadratic? Is it a snake? Is it a square root graph? What kind of model is this? And if you're not doing these problems in a vacuum, like in a chapter just on exponential functions, then you're going to have to be really good at recognizing those patterns. In this case, the thing you're looking for is the x that is in the exponent. That is telling you that this is the graph of an exponential model. So I begin by recognizing that that's the model I'm talking about, an exponential model. The second thing that I want to notice is if it is an exponential growth or an exponential decay model. Remember how we could tell from our previous slide? Well, that's right. We would look at the base. If the base, in this case 3, if the base was bigger than 1, what did that mean for our model? Well, that's right. It was growth. So if we have an exponential growth model, we know the basic shape that it's taking on looks something like this, with 3 easily accessible points. Let's get those points. Our first input that we like is -1. If we input -1 into that function, y equals, let's just do 3 to the x for now, before any transformation, then 3 to the -1 is really 1 over 3, right, the reciprocal. What about 0? Well, if you put 0 in for your input, 3 to the 0 is 1. So far we had -1, 1/3, 0 at 1. And at 1 itself, for an input, we're at 3 to the 1, or 3. So that's when we're shooting up here to 3. So we have our 3 key points, and we also notice that as x goes to the left forever, as our x values get smaller and smaller and smaller, the y outputs are approaching 0. The horizontal asymptote, thus, is y equals 0. So with this information in mind, along with the graph, we're going to get started and draw our transformation of this function. So let's do it. We notice here, if you remember from graphing transformations, that if a number is being added or subtracted to the entire function at the very end here, it could technically be at the beginning, but that would look kind of clunky. That is telling us that we have a vertical shift. Feel free to look up transformations of functions in other videos if you need help practicing those, right? But vertical shift here of 1 unit, and is it going up or is it going down? That's right, it's going down. because subtraction here means you're reducing your outputs by 1. So that means if I go back to my 3 points that I had for my sketch originally, I would now have a new a new set of 3 points with the input -1 still, the input 0 still, and the input 1 still. Here my outputs are changing though, because my y values have decreased by 1. So instead of 1/3, 1/3 minus 1 is really 1/3 minus 3/3, so that's -2/3. Let's plot that point, see where we are. At -1, we'd be down around here at -2/3, wouldn't we? What about at 0? Well, at 0, we were originally at an output of 1. If we've now shifted this graph down 1 unit, 1 minus 1, that's right, it's 0. So our input 0 gives me an output of 0. Kind of boring, but okay. What about the input of 1? Well, originally the input of 1 had an output of 3. But if we've shifted the graph down 1, then it's now located at an output of 2. So at an input of 1 for x, we get the output of 2 for y. And now we can see this does look, in fact, like exponential growth. We can connect our dots in that type of growth pattern. So it's increasing from left to right in a curvy manner, shooting up pretty rapidly. But notice also that it has a horizontal asymptote. The question is it still at 0? And clearly you can see we've gone beyond 0. We've gone below 0, haven't we? Yeah, because our horizontal asymptote was the equation y equals 0. So if our y values have each decreased by 1, then 0 decreased by 1 is at, that's right, -1. So our new horizontal asymptote should be located at y equals -1, meaning that my graph is approaching the y value -1 as my x values get smaller. At this point, now that you've shown the 3 key points that we end up at, along with the asymptote, you are almost done with your graph. The last question that they asked about was, can you tell us the domain and the range? Well, domain, try it on your own and come back. Okay, domain is all x values or inputs which are allowed. Notice here that any input is okay. You can raise x to negative powers you can raise 3 to negative powers or positive powers or even 0. Any input is allowed. So -infinity to infinity is definitely our domain. But our range is a different story. There are some outputs that we never reach, and that is dependent upon where our horizontal asymptote is. So in this case, we moved our horizontal asymptote down from 0 to -1. So now all of our outputs are any y value which is above -1. In other words, parentheses -1 toward infinity. All right, so we've just done an example together. Maybe you tried it by yourself, which would be better. But we've just done an example of an exponential graph that has been transformed. The way to do that by hand is to know where it starts with 3 key points along with its asymptote, and then to recognize its domain and range after performing the transformations. So in order to really become a master of those, you'll need to practice at least 3 of them in a row and get them right before you really feel comfortable. So make sure you do enough practice on those. Let's head over to another type of model that we're going to transform in example 2. Here we're asked to graph y equals, or g of x equals, the logarithm whose base is 1/2 and whose argument is x minus 1. So we would begin by recognizing that this is a logarithmic model, not exponential. We haven't talked a whole lot about logarithmic models and where they're useful in real life, but I can tell you a couple of examples. The Richter scale, which measures the magnitude of earthquakes, it depends on logarithmic models. Another one that in real life, the pH scales of acidity and alkalinity, or how basic your different chemicals might be, that depends on a logarithmic model. Even sound decibels and loudness is measured by logarithmic equations. So these are very, very useful. And the difference, again, between exponential and logarithmic, besides the fact that they're inverses of each other, are how fast they're growing or falling, because exponential is going to happen really quickly, and logarithmic is going to take its sweet time. Okay? So let's take a look at the base here. It's telling us something important. Here the base is 1/2. And whether it's exponential or logarithmic, the base itself will help us to know if it's decaying or growing. Okay? So because our base here, let's back up a bit, because our base is between 0 and 1, what did that tell us about growth or decay? Can you remember? That's right, this would be decay. So it is a logarithmic decay model, which means my graph, if I was doing a sketch, instead of a logarithmic growth model, this is logarithmic decay. And feel free to go back to our first slide if you need to review what the shape should look like. It'll have three easily accessible points that we can find by flipping the normal ordered pairs that we had for exponential models. So instead of -1 for my input, 0 for my input, and 1 for my input, I'll make each of those my outputs. So -1, 0, and 1 are now my outputs. Instead of 1 over b for my output, it's now my input. Instead of 1 for my output, it's now my input. And instead of base b, it's now going to be for my output, now it's going to be my input. So in this particular case, if our base was 1/2, the reciprocal of 1/2 is 2 over 1, or 2. So that's like, for example, 2, -1. That's this third point. What about 1, 0? Well, we can see that on the graph. That would be the middle point. What about the base and 1? Well, the base is 1/2. So when x is 1/2, that would be around here, we're at the output of 1. We also noticed originally a vertical asymptote at x equals 0. So with the picture in mind and the key points and asymptote in mind, we are in good shape to transform this graph. Let's do it. So we begin by recognizing the transformation that we're dealing with is happening inside the function. So it's not a -1 at the end, which would be a vertical shift down. Instead, it's a -1 next to x inside the function, which meant we have a horizontal shift. In fact, we're shifting to the right. It's counterintuitive, isn't it? We're shifting to the right 1 unit. A horizontal shift to the right 1 unit, which would mean that my x values, my inputs, should increase by 1. So now we're at 3, -1. We're at 2, 0. And 1/2 plus 1 is 3/2, or 1.5, for an output of 1. Has my vertical asymptote changed? Well, it's an x value. Have my x values changed? Yes, they've moved to the right 1. So I've added 1. I've increased them by 1. So this would be at x equals 1 now. Let's put that on the graph and see what we have. At +3, we should be at -1. At +2, we should be at 0. And at 1.5, which is around here, we should be up at 1. We should also have a vertical asymptote, a break in the graph, right, at x equals 1. And this should be decaying in a logarithmic manner. So it should look something like that. Sorry, it's a bad sketch from my angle here. All right, so something like that should be what's happening. Could you go ahead and take a moment, pause the video, and do your domain and range on your own? Okay. All right, so the domain would be all inputs which are allowed for x. So in this case, there are in fact restrictions, right? We can see in the graph that there are some x values which we never input. In fact, the x values appear to be always to the right of our vertical asymptote. So that would be parentheses 1 toward infinity. I'll talk more about that in a moment. What about the range? Well, yeah, I can reach every output. I go down forever and up forever, so -infinity toward infinity is my range of y values that are allowed to be reached. Now, as far as domain for a logarithm is concerned, there is a shortcut. Notice that it had to do with where our vertical asymptote was. And originally it was just at x equals 0, and so my original domain would have been to the right of 0, 0 to infinity. But when I had x minus 1 in my argument, I ended up having a domain of 1 to infinity because it shifted the graph to the right 1 unit. So a shortcut for domain of logarithms is to simply take your arguments and make sure that they're always greater than 0. If you start off there, you can evaluate which inputs are allowed. So in this case, we're saying x minus 1 is always greater than 0, which would mean that my x values are always greater than 1. And that gets us back to our domain, which was right there, 1 to infinity. Well, that puts us in really good shape for example 3. You might want to even try it on your own. Here we go. In example 3, it says, could you find the domain of the logarithmic function g of x equals log base 3 of x minus 8? Well, you could do a graph of this. This is logarithmic growth. So this graph would look something like this if it's logarithmically growing, with 3 easy points. We could find those if we were interested in them, and a vertical asymptote. But what's happened here, I hope you notice, is we've shifted this graph to the right 8 units, haven't we? If we recognize how to transform functions, which would mean instead of my asymptote at x equals 0, my asymptote is now going to be at x equals 8. And my graph will look something like this. So my domain should be 8 to infinity. But even without the graph, we could use that shortcut that I mentioned a moment ago to find out the domain. I could have simply said, anytime I have a logarithm, I know that my arguments, there could be more than one logarithm, that's why I use the plural, must be greater than 0, which would in this case mean that x minus 8 has to be greater than 0, or x has to be greater than, that's right, 8, which brings us right back to that domain. So either way is fine. It's probably faster not to graph it every time, but you really should take the time in your homework and your practice and as you review for tests in the final to always take time to graph and make sure you understand visually what's going on. If you don't want to do it by hand, at least take advantage of the technology, Desmos and calculators, to check yourself. Okay, why is this important? As we get into our next video, in our next section, we'll be talking about solving logarithmic equations. And sometimes you will get answers like x equals 2, which sounds perfectly fine, and you might declare with victory that you have the right answer. However, if x equals 2 was an answer for us, and we had a situation like this, where in our equation somewhere we had log base 3 of parentheses x minus 8, notice what would happen if the input was 2. At 2 minus 8 is negative 6, and that is not greater than 0. So we would have to exclude that potential solution. Now you might be wondering, why would you possibly give me an equation which I can get an answer and it might not actually be an answer? Well, in real life this happens all the time. Let's say there was a new iPhone that you wanted to buy and you were trying to figure out how many hours per week or per day even you'd have to work at your job to afford it. And you come up with your solution at the end and you say, guess what? I can afford the iPhone. I just have to work 36 hours a day. Okay, technically, mathematically speaking, yes, that's possible, but in real life, there's only 24 hours in a day. Similarly, you might get a solution that in theory would work, but in reality, it's not an allowed input. It doesn't make any sense. So that's why we're throwing them out. Okay, hopefully that helps to make some sense when you have to make restrictions. Okay, let's take a look at example 4. Here we're being asked to write an equation of each graph in final position. Okay, so the first thing we want to do is recognize what the equation is referring to. I have the equation y equals 1/2 as my base raised to the x power. So when I look at that graph, I need to think, what kind of model is this? Since x is in the exponent, this is an exponential model. Is it exponential growth or decay? That's right, it is decay. And that's because our base is between 0 and 1, right? Our base here is 1/2. So if it's exponential decay, originally our graph should look something like this, with 3 easily accessible points. What were those points? When x equals -1, 1/2 to the -1 power is really its reciprocal, and the reciprocal of half is 2. So at -1, we're up here at 2. What about when x is 0 for my input? Well, 1/2 to the 0 power, anything to the 0 power, is really 1. So that's at 1. And what about when x is 1? Well, 1/2 to the first power is just the base itself, 1/2. So at x equals 1, we're here at 1/2. Okay, what else do we see here? That's right, we see a horizontal asymptote when y equals 0. So we keep this in mind, and then we're going to transform this graph. This was the graph of y equals just 1/2 parentheses to the x power. Let's do our first transformation now. The first transformation, it says, can we stretch this model vertically by a factor of 2? So this is the first one that we're going to take care of. In order to do that, we need to remember what a vertical stretch means. It literally should stretch out your picture vertically. And the reason it's a stretch and not a shrink or a compression is because our number is bigger than 1. Okay? If that number was 1/2, it would be shrinking or compressing the graph instead. So for a vertical stretch, remember what that meant practically? It meant that we had to multiply our y values, because it's a vertical stretch, by that number, in this case 2. So what would that mean practically for my points? Well, my y values would be doubled, wouldn't they? I could have stretched it by a factor of 4 and they'd be quadrupled. That would go even faster. So at -1, I multiply my y value 2 by 2 and get 4. So at -1 here, now I'm at 4, so I'm up there somewhere. What else happens? Well, at 0 for an input, my output instead of 1 is 1 times 2, or 2. So at 0, I'm now at 2. And what else is happening? So that was the location 4 there. At 1, I have my output of 1/2 times 2, which is just 1. So at 1, I'm now up here at 1, and my graph is now stretched out just a little bit by a factor of 2. In other words, my y values just got doubled. Did that affect my horizontal asymptote? Let's see. So my horizontal asymptote was originally at y equals 0, but if I've doubled 0, does that change anything? No, 0 times anything is still 0. So my horizontal asymptote is still at y equals 0, so that part's still the same. But what has changed is my equation. To multiply the y values by 2, your equation would have to have a 2 somewhere. But where? That's right, at the beginning. Because at the beginning would mean I'm multiplying the entire output by 2. The output is my y. So 2 times parentheses 1/2, close parentheses, to the x power. That would be the equation at this step. Now the reason I recommend writing out your points each time is now you can test if you have the right equation. You can say, for example, at the input of -1, do I really get the output of 4? Let's try it. 1/2 to the -1 power is the reciprocal, or 2. And 2 times 2 is 4. That checks out. 1/2 to the 0 power is 1, and 1 times 2 is 2. That checks out. 1/2 to the first power is 1/2, times 2 is 1. That checks out. So I know with confidence that I have the right equation for that transformation. Let's hit up our third and final transformation. Our second transformation, I should say our second transformation, but our third part of the problem. So our second transformation is a shift to the right 3 units. This is also known as a horizontal shift if you go left or right. So if I'm going to the right 3 units, practically speaking, that means this graph that we left off with, the white graph, is now going to pick up and move to the right 3 units. So 1, 2, 3, somewhere over there. 1, 2, 3, somewhere over here. And 1, 2, 3, somewhere over here. So this graph is now looking something like this. Okay. But how do we show that in our points? That would mean that the x values are increasing by 3, aren't they? So our point should be -1 plus 3 is 2 at the output 4. 0 plus 3 is 3 at the output 2. And 1 plus 3 is 4 at the output 1. Those should be my new points after this transformation to the right. Also, my horizontal asymptote is a y value. So changing the x's shouldn't change a horizontal asymptote. So that should stay at 0, at y equals 0. Okay. As far as the equation is concerned, do you remember how to do that with a transformation of a horizontal shift? That was the counterintuitive one, if you remember. It happens inside the function next to x values, but if you subtract from the x, you're really moving it to the right, and if you add to the x, you actually move it to the left. So in this case, if I want it to move to the right, my equation should be y equals the 2 from the stretch in front, times the base, which is still 1/2 in parentheses, but in my exponent, I could put it in parentheses to be super clear. I'm going to put x minus 3. So that's the one that was counterintuitive when you first learned about transformations of functions in your previous classes. You might need to look those up again if you don't remember why that is happening. Okay? So at this point, I want to test, do I have the right model? And to do that, I simply plug in my inputs and see if it spits out the right outputs. So for example, at the input of 2, 2 minus 3 is -1. Reciprocal of 1/2 is 2, and 2 times 2 is 4. And you can check each of these on your own. They will all work. So we've in fact found the equation in its final position. Y equals 2 times parentheses 1/2 all to the x minus 3 power. Technically, you don't have to use the parentheses for the exponent, but it's highly recommended, especially if you're using technology, because you want to tell your calculator or Desmos, whatever you're using, that this is all in my exponent. Okay, one more example, see if we can actually put this to use. Here we go. Example 5. Find an exponential model function which contains these points. Now you've done this before for lines, I hope you remember. If you had 2 points that were on a line, you would say, well, what's the equation of a line? Like y equals mx plus b. You'd plug in your points until you found your slope m and your y-intercept b. Nothing has changed here. It's just a little more difficult. This time what we're told is we have 2 points. We have a point 0, 1, so maybe up here. And we have a point -2, 1/9, so maybe down here. But instead of connecting these points with a line, we're told to make an exponential model. And this would be growth, it looks like, because it's increasing from left to right. So I apologize, it should go through the point. Okay. So something like this is happening, but prettier. Okay, so we should have an exponential growth model going through those 2 points. Now to do this, we can't use y equals mx plus b, because that would be a line. Instead, you'll need to memorize these. You'll either use f of x equals some a, some constant, which is stretching or shrinking your graph, times b, your base, to an exponent x, your variable, okay? So that's the one we're going to do in this example. In a future lesson, a future video, I'll show you how we could have done it with the other model. A of t, so amount depends on time, equals a sub 0, the initial amount when time is 0, because anything to the 0 power is 1, so you're just left with that amount, times e, Euler's number, to the k times t, where k is your growth or decay rate, negative for decay, positive for growth, and t is time. That model is very useful, especially in financial applications or population applications. So in future videos, we'll be using that one quite a bit. But it turns out that the first model is actually the easiest in this case. So let's get started. The first thing I would do is use my first point, 0, 1. And because I gave you a point that had 0 for an input, you should be very thankful. This turns out to be an easy problem, okay? At 0, 1, that means that my input, so let's write out our function here, the output is f of x. It's supposed to equal some constant a times some base b to the x power, right? If I input my point, let's take a look at what that would mean. If my input is x, so x is 0, I'm going to now replace this x with 0. And if my output is 1, I'm going to replace my output, f of x, with the appropriate output. In this point, it's 1. So that's going to be right here. So now that I have 1 equals a times b to the 0, if I understand what b to the 0 is, life is good. Because anything to the 0 power is simply 1. So I really just have that 1 equals a, or a equals 1. Well, just like for a linear model, if you were trying to plug in points to find your slope and your y-intercept, m and b, similarly, we're plugging in points to find our constants a and b. We've just found our first constant, a. So our model has now become improved. We've improved upon our model. Our model is now f of x equals a, but a is 1. So we're not actually stretching or shrinking our graph. That's what that's saying. Times b to the x. Our job now is to find b. That's what we're after. Let's do it. So we're going to plug in our second point. Our second point was when x is negative 2 for input, our y value, our output, should be 1 over 9. See if you could try this one on your own. Pause the video, plug it in, and see if you can solve. Okay, let's see how you did. If you truly plugged in into this function right here, if you truly plugged in your output of 1/9, you'd have 1/9 on the left side. You don't really have to multiply by 1 because it's still itself, so feel free to just do b to the x here. The base is what we're solving for, but here the input, x, is negative 2. So there's my input and there's my output. Same thing as last time, but we're using the improved model. This is super nice because we know what to do, right? 1 over 9 is really equal to what? That's right, 1 over b to the second power. And I could solve this ratio equals a ratio, otherwise known as a proportion problem, by simply cross-multiplying. Another way of saying that is you could clear your fractions by multiplying both sides by the least common denominator, 9b squared. But cross-multiplying is easiest. 1 times b squared is simply b squared. 9 times 1 is simply 9. Now I could solve this using the square root property. b could either be positive or negative square root of 9. But we know what the square root of 9 is, don't we? Yep, it's 3. Where's my white? There he is. It's 3. Now here's something interesting. You got a positive or a negative 3. Now maybe you forgot the negative 3 and you're like, oops, I forgot the plus or minus. In this case, forgetting the plus or minus might actually be beneficial because it turns out, you may not have noticed this on our first slide, but your bases are always bigger than 0, meaning negative bases are not allowed. So we're going to actually only write 3 as our answer here. Well, now that we have our answer for 3, oops, let's use a pen instead, not an eraser. Writing with an eraser is not too easy. All right, so let's do b equals 3. Now that you have your a equaling 1 and your b equaling 3, you have your model. It's supposed to be an exponential model of the variety f of x equals some constant a, which was 1, times some base b, which was 3, to some exponent x. Now we have a model that could be used to find any other point on this trajectory. So when x equals 2, we're at 9. When x equals 3, we're at 27. Now granted, this is an easy exponential model. They get much more complicated, especially when we're dealing with financial applications or population growth or decay. Okay, so I wanted to start you off with an easy one, but these same steps will be useful in setting up and solving any exponential model. All right, so we've done a lot today. We've graphed, we've done models, we've talked domain. Remember, this isn't your knowledge until you've applied it. So make sure you practice because math is not a spectator sport. See you next time.